Get the sign-in sheet going. Everybody make sure you get signed in. What's the date? 12th? S'il vous plaît. Who can tell me what an acute angle is? Say again? Less than 90. And an obtuse angle? Greater than 90. Now, who can tell me what an oblique triangle is? No, they can have, you can have two of the angles are the same. An oblique triangle is basically any triangle that's not a right triangle. Okay, it means that it's either going to have three acute angles, like so, or it's going to have two acute angles and one obtuse angle. But it's not going to have a right angle anywhere in it. And that's what we're going to start looking at today, our oblique triangles. Right triangles are very nice. They're easy to work with. You know, we get all the trigonometric functions and coordinates, and they make everything really easy to work with. But right triangles almost never happen in nature. How many of you have ever gone boating? How many times have you gone up the river and found two streams crossing? Or even, not even necessarily at right triangles, just have one stream one river cut across another one. You don't generally find four-way intersections like that in nature. You find three-way intersections, or what we would describe as a fork in the road. The way roads used to develop, they would just sort of evolve organically, not by some central planning where someone laid everything out on a nice square grid. They would just, roads would develop wherever people happened to walk a lot, or rode their horses past a lot, or drove their wagons a lot. And where they followed the paths of people before them, and where two paths would meet, they would meet usually at an acute angle or at an oblique angle, but they would meet and form a fork in the road. Look at veins and how they develop in leaves or blood vessels or rivers and streams. And the point is, you find out, you begin to realize very quickly that right triangles, while they're very handy and convenient mathematical constructs, they don't really reflect nature very well. They help us analyze nature, but a lot of times you're going to run into a situation where you need to solve a triangle that simply is not a right triangle. And towards that end, we are going to develop the law of sines and the law of cosines. Now, if you want to follow along in your book on page 272, you'll find where they've drawn these 5 triangles for you. And they describe all of this very precisely and very accurately, but they also don't really make it very intuitively understandable of what's going on here. The bottom line is, in these 3 cases, we're going to use the law of sines to solve to solve these triangles, figure out the lengths of all the sides and all the angles. In these two cases, we're going to have to use the law of cosines. Now, what's the difference? Well, in these two cases, you know, in all of these, the way I've drawn them matches the book. Everything in red is unknown, and what you see in blue is assumed to be a known value. So in this case, you know the side C, and you know the two angles A and B. Or you know side C, and you know the two angles A and C. Okay? Doesn't really matter which is which. If you know one side and two angles, then you can use the law of sines to solve for the rest of the triangle, to determine the other two sides and the third angle. In point of fact, just right off the top of my head, just real quick, let me ask you all a question. How would you figure out the third angle in either one of these cases? Where you know two angles of a triangle, how would you figure out the third angle? Once you know two angles, you know the third one because the sum has to equal 180. So if you subtract the two that you know from 180, that gives you the degrees of the third angle. We're going to see that we can also figure out very quickly what the other two sides are. Now, over here, you know all three sides, but you don't know any of the angles. Well, fact is, I mean, you can kind of intuitively see it in your mind. If you have three sides defined, then that defines the whole triangle. It can't be any other triangle. Okay? And now, we may not know the angles, but we'll be able to figure them out with the law of cosines easily enough. The big difference that I want you to see between these two sets is between this one and this one. Now, in both cases, you know two sides, but you only know one angle. In this case, you need the law of sines to figure out the remaining parts of the triangle. But in this case, you need the law of cosines. The difference is when you know two sides and only one angle. If the angle is included between the two sides, then you need the law of cosines. If the angle is opposite one of the two sides, it's not included between them, then you need the law of sines to figure out the rest of the triangle. That's the big difference. There is one thing I would point out, just because it's interesting to think about. In this case here, we know all three sides, which defines one triangle, and only one triangle. And then we have to figure out the three angles. What if you knew all three angles, but you didn't know any sides? Could you then solve for a triangle that would give you the three sides? No, you can't, because if all you have defined are the three angles, then you can make those three sides as big or as small as you want to make an infinite number of triangles. So if all you know are the three angles, then what you have defined is a family of congruent triangles. Congruent? Am I using the right word? Somebody look it up and confirm that. Congruent is, similar is where they're actually, similar is where all the angles are the same and all the sides are the same. Congruent is where all the angles are the same, but the sides are different. Yeah. Okay. You sure? And so I got it backwards? Okay. Everybody look it up and confirm for yourself before you take my word for it. But the point is that if all you know are the three angles, then there are an infinite number of triangles that they can make. Now, I'm going to go ahead and write the law of sines up here for you so you can see where we're headed as we start developing this. The ratio of the sine of the angle divided by the opposite side is equal for all three angles and sides. You'll notice that when I labeled all of these triangles, I always labeled the angle opposite the side of the same name, distinguishing angles and sides from by making them upper or lower case. But side B is always opposite angle B, side C is always opposite angle C, side A is always opposite angle A. That's a standard way of writing all of this, which makes the law of sines fairly easy to remember. Now we're going to look at how to use the law of sines to solve some of these triangles. But before we do, I want to work through the derivation of the law of sines so you can all see where it comes from. So let's start. And you want to follow along. This is on page 277 in your book. They work it out for both cases of an oblique triangle, with where one has with all three acute angles and one with an obtuse angle. But honestly, I think we worked through it once. You'll be able to see it the rest for the other case all on your own. So let's start with just a generic triangle, not a right triangle. Which side do they put down? B. There's B. Now, we start from this apex and we divide this triangle into two separate triangles, both of which are now right triangles. And the length of this line is h for height, the height of the triangle. Now, think back to your definitions of the trigonometric functions. A times the sine of this angle C will give you that height. Remember from the definition of your trigonometric functions? Or we could just write the sine of the angle C is equal to the height divided by side A. All right? Now, by the same argument, we know that C times the sine of A is also equal to the same height h. Everybody see that? This hypotenuse of this right triangle times the sine of this angle gives you the height h, the opposite side. Same over here. C times sine of this angle gives you the same height, h, which means we can set both of these equal to each other because these are both equal to h. So we've got A times A sine C is equal to H, which is equal to C sine A. And if we divide both sides by C and then both sides by A, we end up with sine C over C is equal to sine A over A. Sine C over C is equal to sine A over A. And of course, my choice of which side to put on the bottom was arbitrary, so I could easily rotate this triangle and repeat the same derivation and come up with the same relationship between sine of B and side B, and either one of those other two. Does everyone see how that works? Do we have any questions yet? Does everybody understand what's going on here? So this is the law of sines, that these ratios will be equal. So let's look at some examples. You know what? Before we do, I forgot. I wanted to ask, does anyone have any questions from the homework you've been working on so far? Any homework questions? All right. Well, does everyone remember that you have until Friday to turn in any late homework or to make up any exams that you missed? Everybody on track to get that done? Because you look at your grades on Canvas right now, anything that you have not turned in is just not being counted. But at the end of the semester, any of those homework assignments that you did not turn in, they will turn into zeros, and you get a lot of zeros popping into your grade average, it's going to drop precipitously. That means abruptly. So, make a point of getting any of those homework assignments that you haven't done. Go check on Canvas, see what's not there yet. Get them done, get them turned in. All right, let's see if any of these examples are even interesting. Well, we'll start with example 1. Solve the triangle. A is 40 degrees, B is 60 degrees, and A is 4. units. So, A, B, C, A, B, C. Only they gave us numbers for A is 40 degrees and B is 60 degrees. And everyone, I load up with these things and they all migrate to one end. Okay. A is 40, B is 60. Degrees, not radians. All right, well, right off the bat, what we're gonna be doing is we're gonna be solving for C, for B, and for angle C. And right off the bat, what is angle C? It's got to be 80. The other two add to 100, and all three have to add to 180. So C, without even touching a calculator or putting pen to paper, we've already got C solved, 80 degrees. So, now all we need to do is solve for these sides. Well, we know from the law of, well, let me follow the book just to make sure. Sine A over, yeah, okay, we know sine A, which is 40 degrees. I'm going to move over instead of messing up where we're putting all the answers. So we've got sine of 40 degrees divided by 4 is equal to the sine of 80 degrees divided by C. Well, we can just do some quick algebra and we get C is equal to 4 sine 80 divided by sine 40. Somebody with a calculator, punch the buttons and do the arithmetic. But don't everybody do it at once. You're really going to make me call people by name, huh? Oh, sure. Yeah, let's do that. Starting from here, multiply both sides by C. And they cancel. Now multiply both sides by 4. And they cancel over here. Now divide both sides by C, well, by sine 40, because we're solving for C. And they cancel over here. We end up with C equals 4 sine 80 over sine 40. Okay? And that's a good thing that's a good question to ask, because it's, especially if you've done a few, it's very easy to just look at this and go, okay, and just do the algebra in your head, and that's how you make mistakes. That's how I make mistakes. How I usually end up embarrassing myself in front of the class. You know, things like transposing congruent and similar. So yeah, it's definitely always well worth the exercise to go through and make sure you understand each step of how you do things like this. So Who did the arithmetic? 6.12. I think 2 decimal places is enough. So, all right. Huh? Well, all right. 6.13. Anybody else? All right. Then all we got to do now is figure out B. Right. We've got, that's now 80 degrees. And this is now 6.13 to whatever units. So, how do we just repeat the process and solve for B? So, we know that sine of 60 degrees divided by B is equal to, pick one. Which one do we want to use? So, multiply both sides by B. And we get sine 60 is equal to B sine 40 over 4. We multiply both sides by 4. And we have 4 sine 60 equals B sine 40. And being careful to remember that it's B that we're trying to get to solve for, divide both sides by sine 40. They cancel, and we have B is equal to 4 sine 60 degrees over sine 40 degrees. And again, somebody with a calculator do the arithmetic. I'm sorry, say again? 5.39. And we have solved. We've solved the triangle. We still haven't solved the problem of my erasers migrating all the way to the other side of the room. 5.39. Any questions?
Do we use Pythagorean's theorem on this?
We used the right triangle when we derived the law of sines. Now, we're going to use a variation of Pythagorean's theorem when we do the law of cosines, but it's not going to be an even. We're going to have to add a little bit extra to the end, which is where the cosine comes in, because it's not a perfect right triangle.
Yeah.
But now, any questions yet? Well, then let's do another example. This time we're going to go with a triangle where we have 2 acute angles and 1 obtuse angle. Let's. All right, we got A, B, and C. Oh wait, they tell us what C is, right? 5. And we know 15 and 35. So we've got to solve for angle C, sides A and sides B. So, first thing off the bat, what is angle C? Say again? 130. Let's see, that's 50 plus 130 equals 180. All right, 130 degrees. So, which one do we want to solve for first, A or B? All right, multiply both sides by A. They cancel. Multiply both sides by 5. And these cancel, and now divide both sides by sine 130. These cancel, and we have A is equal to 5 times the sine of 35 degrees divided by the sine of 130 degrees, and that equals 3.74. Really? Okay, you know what? That does make sense, because it's going to be shorter than 5. All right. And again, just out of habit, just as a matter of good practice, once you've gotten an answer from your calculator, look at it and see if it makes sense. I don't know what buttons he pushed, but I know that if he came up with 20-something, that can't be. It just cannot be. So, it's always good to think about the answers you're getting. What are they supposed to be? What do they mean? Do they make sense? And now let's finish this up with the solving for B. We know that sine of 15 degrees divided by B is equal to sine of 130 degrees divided by 5. Solving for, multiply both sides by 5. And they cancel. Multiply both sides by B. And they cancel over here, and then divide both sides by sine 130. They cancel over here, and that leaves us with B is equal to 5 times the sine of 15 degrees divided by the sine of 130 degrees. And somebody with a calculator, give me the answer. 1.7. Again, look at the picture. Does that make sense? Yeah, it does. So how many are getting the idea that maybe the homework problems for this chapter aren't going to take very long? What are they? Ah, okay. They're calling this an ambiguous case. All right, let's step through this. We've got some time. And up until now, we've presumed that we knew we were working with a triangle. They're talking now about case of what they call case 2 side-side A angle, SSA, on the first page of the chapter. And they're saying this could be considered an ambiguous case. Well, in fact, we have basically up to this point, we've been assuming that we knew that what we were looking for was in fact a triangle. But let me make sure I draw this correctly. They're talking about side-side angle. They're saying, okay, you know this length and you know this length. And you know an angle here. You don't know this angle or this angle. Now what they're saying is that if you don't know what this angle is here or this angle is here, then, but you are limited to an angle here and these two sides, then the result may be a triangle, or it may be more than one triangle, or it may be no triangle at all. All right? So, let's look at how this might be. And they call this the ambiguous case. Just to reference it to your book, it's case 2 SSA, side-side angle, on page 272. I hope I didn't misspell that. If I did, correct it in your notes. I want to do this a little more room to work with here. So, we're going to start with our friend the right triangle. And we're going to drop a perpendicular and make a right triangle with sides B and C and height H. So C is the hypotenuse of this right triangle. And we know that, well, this is angle B that's unknown. No, this is angle A that's unknown. This is angle B that's unknown. We know that C times the sine of A must equal H. Yeah, they swapped letters on me here, so bear with me. Okay, in this case, they're saying, yeah, they're doing me. They've completely reversed everything from the way they've been labeling it. So, what they're saying is, we know this angle. I'm sorry, say again? I'm on 274. No, they've got the letters. I've been trying to stick with the same, calling the bottom B, this one C, and that side A, and the angle's the same, and that they've swapped them around. They switched them around on me here. But they're saying that we know, they're saying that the known values are they know that the known values are A. Now let me they don't specify this here, so let's figure out which ones they say are known. A and B and angle A. So I'm gonna and they're saying that we know this length A and we know this length B. And we know this angle A. So, all right. Now that's the parts we know. We know A, B, and A. We do not know length C. We do not know angle B. Now, this is case 2, side-side angle, where the angle is not included between them. And this is the one they call the ambiguous case. Start off with, we know that this height, h, is b times the sine of a. Well, you can just tell by looking at the picture, if a is less than h, then if a is shorter than this height, then there is no angle that will allow it to reach this opposite side here. And so the information tells us that no triangle can exist with this angle and these two sides. Right? Or no solution. Now, if A is exactly equal to H, then you get one and only one solution. One triangle. And that's a right triangle. But if A is greater than H, then you get two solutions. Okay? Suppose A is greater than H. Then you get one solution here when it first meets the bottom. And you get a second solution here. So you will get two separate triangles, two separate solutions if A is greater than H. What irritates me when they swap that, when they do that, they start off in the book with one standard way of labeling everything, and you think it's going to be consistent the whole way through, and then, anyway, enough belly aching. Learn to swim in the water where you live, right? All right, let's, does everyone understand this? Do you see how you can end up with, well, with literally with three cases? The one case where there's no solution, the one case where you get one and only one solution, it forms a right triangle. But if A is longer than that height, then you're going to have two solutions. So let's actually they do. They give us three examples here for each case. So let's take it one at a time. Let's work through each of these examples right here. See if that might solidify some of this. So in the first case, they give us A equals 2, C equals 1, and angle C equals 50 degrees. So, we know we've got 50 degrees. A is equal to 2, C is equal to 1. So, we don't know this angle, we don't know this angle, we don't know this length. But we do know that sine of 50 degrees divided by 1 would have to equal sine of B divided by 2. So what is 2 times the sine of 50 degrees? .53. 2, does everybody see how I got to that solution? Multiply both sides by 2. And they cancel. So, we're saying that sine of angle B, this unknown angle, has to equal 1.53. How is that possible? What is the range of the sine function? Somebody? -1 to 1 is the range of the sine function. There's no angle that will produce a sine of 1.53. So sine B cannot exist. And we have no solution. There's no angle. We could also confirm that by simply taking what's 2 times the, we just did. 2 times the sine of 50 is 1.53. This is only 1. So this angle, this line would have to be a minimum of 1.53 long. You see what I'm saying? Multiply this leg times the sine of this angle gives you 1.53, which would be the minimum length of the opposite side. So, no solution. Well, in this case it is, yes, but we actually came to that from 2 separate approaches. One, we just naively applied the law of sines and found that in order for that to be true, the sine of this angle would have to equal 1.53. Okay? Which if you go back to the where we derived the law of sines, that's basically what we were doing. We're setting the sine of each angle equal to the height of the triangle. Now, then the next one they give us is the example they work out. They're going to give us an example where there's one and only one solution. So let's work that one through. Say again? Yeah, example 4. Now, we've got hold on. 3, 2, 40 degrees. So sine 40 over 3 would be equal to and we're solving for this angle B, sine of B over 2. All right. Multiply both sides by 2. Those cancel. So what is 2/3 times sine of 40? Okay. Now, what that tells us is that the sine of the angle B is equal to 0.43. So, somebody give me the inverse sine of 0.43. What does that give us? 25.47. All right, 25.47. Let's be careful here. Say again?
I used the real number. I didn't round up first.
25.37. Anybody? I've got 25.37 going once, 25.37 going twice. Last and final call. Yeah. Anybody want to bid again? Going once, twice. Sold to the man in the red shirt. 25.37. We need to be careful here. Because just a minute ago when I was working this out, I said, in order for there to be just one and only one solution, this had to equal the height, h. And it would form a right triangle. Well, this is not a right triangle, but they're saying there's only one solution. So how can that be? A is longer than B. Think of your unit circle. We've got this solution. And that gives us this value of sine. Where else would we get that same value of sine? Point is, this comes down here 3 times 3. If that's 2, this is 3. We got 25.37. What would this solution be? What's 180 degrees minus 25.37? 154.63. Well, what if we moved this from 25, we moved it all the way out here to that 150 something? Yeah, this could no longer be 40 degrees. Point is that it would put the other end of this side going off away from your other side. Say again? Yeah, well, see, I've done lost track of which side is A, which side is B, and which side is C. So, which side? The point is, this side is the shortest of the 3. Okay, so there's one and only one solution that's going to give you a triangle. All right, so you figure out for yourself which side is A, which side is B, and which side is C. But when this side is the shortest one, there's only going to be one solution. All right, now let's look at an example where we get 2. Say again? Are there any questions before we go on? I would like to. All right, let's look at a case where we have 2 solutions. Now, here we've got B is equal to 8. A is equal to 6. And this angle is equal to 35 degrees. A. Now, what we don't know is the length of C or the angles C or B. We know this side A is 6, and we know that the angle A is 35, so we start with sine of 35 degrees divided by 6 is going to be equal to, we know side B is 8, so it's going to have to be equal to the sine of angle B divided by 8. We multiply both sides by 8. And that's equal to sine of B. So, what is 6 times the 30 sine 35? 0.76. Really?
Yeah, that's what I got.
Wow. Yep, that's what the book says too. Oh. Yeah, you know what? Never mind. I'm going to go back to sleep. Wake me up next week. This is the sine of the angle B. So we need the inverse sine of this to give us the angle B. Okay, so this would be 49.9 degrees. All right, well, what other angle would produce the same sine here? What's our other solution? (180 minus 49.9)? 130.1 degrees. All right, well, let's work both of those solutions. We've got and we're looking for the length of C and the angle C. Say again? Well, that will depend on which one of these solutions we're using. No. C. We'll get two different values of C depending on which value of B we use. Everybody understand that? Let's solve first using this solution. Okay? If we use B as 49.9, then C has to equal say again? 95.1 degrees. Now, what if C were equal to 130? If B were 130.1, then what would C have to equal? $14.9? Seriously, is that it? Is that the right? Okay. All right. Well, solving it based on b equals 49.9, then we get sine of 95.1 divided by c is equal to, sine of 35 divided by 6. And that gives us going through the steps to solve this, multiply both sides by 6. Those cancel. Multiply both sides by c and divide both sides by sine 35. We end up with 6 times sine of 95.1 divided by sine of 35 is equal to c. And somebody give me the number. $10.42. All right. That would mean our solution is this. And $95.1 and 10.42. Now let's repeat the solution, but this time using B equals 130.1 and C equals 14.9. Then we have sine, sine of 130.1 divided by 8 is equal to sine 35 divided by 6. And, well, that's not going to... Sine 95.1 divided by... No, it won't. All right.
Sine 130.1 divided by c. Isn't it the same thing with just replacing the...
Exactly. I should change this to 14.9. I'm trying to solve for the same angle again. All right. Sine 14.9. 14.9 divided by C. And now that's equal to, again, sine 35 over 6. So multiply both sides by C and both sides by 6. And divide both sides by sine 35. And what do we get? 2.69. So, now we're still going to end up with something about there. like so, where now this angle is 130.1, this angle is 14.9, and this side is 2.7 or 6.9. But now do you see how in this case we got two perfectly good solutions from one known angle and two known sides. But you'll notice that in no case yeah. You know what? I'm leaving it right there. Does anyone have any questions? Yep. Nope. Anybody have any homework to turn in? I'm not going to. I don't want to start the law of cosines now because we only got 5 more minutes.
Pack it in.
Huh?
Pack it in.
All right.